Hello, my name is Adarsh Patil. I'm a third-year PhD student working with Vijay Nagarajan at the university and Nikos Nikolaris at ARM. In this talk, I will present my work that aims to create bespoke coherence protocols for improving reliability and performance of data center systems. In the first part of this talk, I will present DWAY, which aims to use coherent replication to provide improved DRAM reliability and performance. In the second part, I will discuss our ongoing work, which aims to use coherent disaggregated memory to improve reliability and performance of function as a service deployments. I'll now briefly summarize DWAY, which is a unique design point in the DRAM reliability design space. It provides three key benefits. DWAY guarantees improved DRAM reliability. It provides memory performance gains and the ability to avail higher on-demand reliability. We will now delve into how DWAY achieves each of these in detail. Let's start by taking a look at how DWAY provides its reliability benefits. In the real world, growing DRAM error rates are a constant cause of concern, as seen in these numerous press reports. Several field studies have characterized these errors and observed the increasing variety and granularity of DRAM errors. The inverted pyramid here represents the increasing data that is lost if errors occur at that level. DRAM reliability mechanisms over the years have been incrementally adding new mitigation techniques to protect against errors rising up in this memory hierarchy. Starting with SecDev ECC and row column pairing to detect and correct cell and array level errors, to chip-kill ECC to handle DRAM chip level errors, all the way to IBM RAM and Intel memory mirroring techniques to handle channel level failures. However, all these error mitigation techniques are gradually adding performance overheads because of the additional checks that they introduce in the critical path. DWAY brings the insight that having full replicas, not just the ECC code, and keeping these replicas as far apart and disjoint as possible allows tolerating errors arising from anywhere in the memory path. Now let's see this in an example. In a conventional multi-socket system, each socket has a DRAM array co-located with it, and the sockets are connected by a point-to-point cache coherent link. In our example, socket 1's memory array holds cache lines X, Y, and Z, and socket 2's memory holds cache lines A, B, and C. DWAY replicates the data present in each socket's arrays into another socket's memory array. Applying DWAY replication to our example, both socket 1 and 2 now hold all the cache lines in the system in their respective local memory arrays. For detection, DWAY can use existing detection mechanisms like ECC CRC parity, or it can employ even stronger detection-only codes. It can also use diagnostic capabilities like temperature sensors to mark failed components and simply rely on the replica for correction. Thus, DWAY can robustly handle a wide variety of errors arising from faults in any of the DRAM components, from cells all the way to even memory controllers. Next, let's examine how DWAY provides memory performance gains. The second insight that DWAY brings is to use the presence of this replica as an opportunity to improve performance. Let's see this in action in our running example. As shown in the figure here, in today's multi-chip NUMA architectures, a miss for cache line A in the LLC of socket 1 must traverse the inter-socket interconnect, and this incurs high access latencies. However, in DWAY's coherent replication technique, the request for cache line A is routed to the nearest replica. But DWAY must also ensure safe access to the replica DRAM data. For example, if cache line A is held in dirty state in socket 2's on-chip caches, then access to the replica memory should not be permitted. This is to enforce the SWMR invariant of coherence, that is, single writer, multiple readers. For this, DWAY introduces a replica directory, which holds metadata to permit memory access if and only if the replica data is up to date. DWAY introduces this technique that we call coherent replication. It builds hierarchically on top of any existing cache coherence protocols. It maintains the replicas in sync as required for reliability and also provides coherent access to both of the replicas during the common case fault-free operation, and thereby improving performance. DWAY proposes two families of protocols to achieve coherent replication. They vary based on how replica permissions are required. An allow-based protocol, which is a lazy or a pessimistic scheme, pulls permissions on access. and a deny-based protocol, which is an aggressive or an optimistic scheme, pushes the deny permissions. Finally, we explain how Dway provides the reliability and performance benefits on demand. The natural question that arises here from Dway's replication scheme is that of the 2x capacity overhead to provide these reliability and performance benefits. This is as opposed to the 25% that is incurred by today's state-of-the-art DDR5 reliability schemes. The third insight that Dway brings to solve the capacity overheads issue is that we can opportunistically use the idle or underutilized memory that is already provisioned in the system. Several recent works have reported this phenomena of a skewed memory utilization. That is, at least 50% of the memory is idle in 90% of the servers. This is because memory resources are often over-provisioned due to peak estimation. Secondly, Dway's overheads are applicable only as and when demanded by the application, unlike today's reliability schemes, which have fixed overheads at design time. For this, Dway provides an interface by which applications can allocate high reliability memory for only certain regions of their memory. Dway provides this interface using a hardware-software co-design approach, with the operating system working hand in hand with the hardware to enable or disable replication when desired. Thus, Dway provides a flexible trade-off between capacity and reliability. This allows deployment of a large number of lower reliability or commodity DRAMs for capacity, while still being able to turn reliability on or off on demand. To summarize, Dway provides improved DRAM reliability over state-of-the-art reliability techniques. It also improves performance using coherent replication in hardware. It accomplishes these goals with a flexible interface that can be deployed on demand. More details are available in our ISCA 21 paper. The simulator source code, the coherence protocol specifications, and all other auxiliary material are available on GitHub and the website that is listed here. For the second part of this talk, we aim to build a suitable coherence protocol that can be used to improve the reliability and performance of function-as-a-service deployments. We now examine the relevant FAS paradigm characteristics. A FAS application is written as a composition of modular standalone functions. The app executes as a directed acyclic graph of function invocations, and this sequence is invoked in multiple stages. An example of a FAS application called the Amber Alert pipeline is shown in this figure. It has two stages. In the first stage, the bounding box function is triggered using HTTP. It draws bounding boxes around all objects in the image. In the second stage, two functions are called, which identifies the type of the car or people located in each bounding box. A notable property of the functions in FAS is that they are stateless, which means that they have no access to the state created by previous invocations. Therefore, they use an object store like Amazon S3 or Azure Blob Storage with a GET or PUT API to store or share data. In our example, the Amber Alert pipeline shares the image, bounding box coordinates, and the pre-trained model through the object store. In a fast execution model, the underlying deployment infrastructure is all managed by the cloud provider. Scaling up or scaling down is accomplished by adding or removing function instances, and the runtime orchestrates and load balances these function instances. As shown in the figure here, the object store and the servers hosting the function instances are all connected by common Ethernet-based network. Our proposal called FastDM replaces the object store with a disaggregated shared memory. The key motivation to do this is to efficiently provide in hardware all the services that are currently implemented in software. The FastDM architecture is shown in the figure here. The servers hosting the function instances are connected to a centralized, highly available memory node with a memory semantic fabric like GenZ or OpenCAPI. The memory semantic fabric provides cache line load store semantics. We use this disaggregated memory to share data between the compute instances instead of the object store. Our proposed architecture achieves several benefits. It can use the low latency hardware caches present on the servers to exploit locality in the access data, as well as benefit from the existing hardware techniques like prefetching. It provides application transparent caching without the need for caching libraries or distributed key value stores, key value caches. It provides implicit data movement using internode cache coherence protocol. It also allows us to use existing shared memory synchronization techniques like mutexes and semaphores to coordinate data that is written into the disaggregated shared memory. FastDM can also reduce overfetch problems by only bringing in parts of the shared data structure that is accessed on demand. Lastly, it allows retention of dirty data in the local caches and avoids having to perform write-backs in the critical path. I will now set out some of the open problems that we are aiming to solve in our proposed FastDM architecture. The figure shows the logical view of memory from our running example. The servers share the same physical memory segment in the disaggregated memory amongst them. Firstly, we aim to answer address mapping and translation questions. How is the shared memory region mapped and translated between independent servers? What are the coordination and communication primitives supported? Secondly, we aim to improve performance. Here, we seek to optimize the internode coherence protocol. Thirdly, we aim to provide appropriate availability guarantees, given that the compute servers and the memory can fail independently and partially. Our approach to solving the address mapping and translation problems draws several insights from the shared memory systems. First, we extend shared memory IPC APIs to allow sharing between function instances. Second, we extend the process of annexation to allow mapping the disaggregated shared memory segment into the fastest function's virtual address space. The diagram illustrates the mapping and translation process. The shared memory segment annexed by the fast function in server 1 and server 2 is mounted at the end of the physical address space. Any request to the address in this extended PA is routed to the Gen Z controller that is sitting on the coherence bus. The OSs exchange messages via RPC to name and identify FastDM memory segments. Address translation is similar to a nested two-level page table. Our goal is to also tailor the internode coherence protocol to improve the performance of FastDM. For this, our insights are driven by examining the sharing characteristics of the fast workloads and using the function execution time as a temporal hint for the sharing vector. Finally, we aim to provide better availability guarantees for FastDM using a non-blocking cache coherence protocol to guarantee forward progress during partial failures. And secondly, provide atomic durability and memory consistency guarantees to tolerate failures. Thank you for listening, and please feel free to reach out to me for any questions.